Welcome to The Explainer. Today, we're diving into what looks like a massive mathematical breakthrough in AI news. We're unpacking a recent paper that targets a fundamental flaw in exactly how we compress artificial intelligence models. Look, if you've been following the sprint toward deploying massive models on standard hardware, you know that quantization is the magic wand making it all happen. But that wand, it's had a pretty severe limitation. Well, today we're exploring a completely new approach called signed symmetric quantization. It's a method that literally flips the script on how we handle weights, granting us accuracy gains at absolutely zero extra inference cost. So, this brings us to the core mechanical problem we're tackling today. Can we actually fix quantization clipping without slowing down our LLM inference? For years, the industry consensus was basically a hard no. You either accept that your model is going to lose some of its crucial extreme values, clipping them off and hurting the model's intelligence, or you introduce complex math to save those values, which entirely bogs down your hardware and slows down your generation speed. It's been this brutal compromise. But what if I told you that compromise was entirely unnecessary?
Here is how we're going to break this down. We'll start with the low-bit quantization problem, explore the symmetric versus asymmetric trap, unpack exactly how signed symmetric quantization works, look at the proof in the performance, and then wrap up with concrete next steps for developers.
Okay, let's dive right into section 1, the low-bit quantization problem. There is this fundamental, honestly kind of annoying quirk of computer science that we hit when pushing models down to ultra-low precision, like 2-bit or 4-bit integer formats. Standard signed integer alphabets always contain one more negative representable value than positive ones. Think of it like a bus, where for some architectural reason there is one extra seat permanently bolted to the left side. By convention, standard symmetric quantizers force the scale parameter to be strictly positive. Going back to our analogy, that means the bus is only allowed to drive in a way that leaves that extra seat permanently stuck on the wrong side of town, specifically in the negative tail of your data. And here's why that extra seat matters so incredibly much. When a group of weights in a neural network contains positive outliers, really important, highly active positive numbers that exceed the fixed positive range of our quantizer, they just get chopped off. They get clipped. Now, at standard high precision, this might just be a negligible rounding error. But at few-bit precision, this clipping introduces a non-trivial L2 distortion. It's a severe mathematical error. You are literally throwing away the most pronounced signals in your model, which fundamentally breaks and degrades the model's downstream accuracy. Which leads us perfectly into section 2, the symmetric versus asymmetric trap. Imagine the painful tug-of-war AI engineers have been forced to accept to deal with this clipping issue. On one side, you've got symmetric quantization. It's incredibly fast, requires very little compute overhead, but as we just saw, it violently clips your data when positive outliers appear, hurting accuracy. On the flip side, you have asymmetric quantization. This method fixes the clipping problem by introducing what's called a 0 point, which shifts the entire quantization grid toward where the data actually lives. It saves your accuracy, sure, but that flexibility carries a massive, measurable runtime penalty. Just look at the real-world impact of that runtime penalty. According to the source research, running a 4-bit model on an AMD EPYC Turin CPU highlights this gap perfectly. The standard symmetric format uses up to 9% less memory and delivers up to 2.45 times higher throughput than its asymmetric counterpart. Why? Because the asymmetric penalty stems from per tensor or per group 0-point arithmetic. Having to constantly calculate that 0 point disrupts factorization patterns and massively increases register pressure on modern hardware accelerators. So historically, you're stuck choosing between a smart but slow model or a blazing fast but slightly dumbed down model. But what if we just reject that premise entirely? Let's get into section 3, signed symmetric quantization explained. This entire breakthrough hinges on one brilliant mathematical realization from the researchers. They proved that negating the scale of a standard symmetric quantizer is analytically equivalent to a unit 0-point shift on the same signed integer alphabet. What does that actually mean in plain English? It means that just by allowing our scale parameter to take a negative value, by literally just flipping a sign, we gain the exact grid-shifting power of those slow asymmetric formats, while keeping the blazing fast computational simplicity of the symmetric ones. This is formalized as the signed abs max grid. It is a ridiculously lightweight scaling rule. We just evaluate the dominant outlier tail of each weight group. If the positive outliers are exceeding our range, we simply flip the scale sign. Remember our bus analogy from earlier? Instead of leaving that extra seat stuck on the negative side of town, this single sign bit lets us instantly drive the bus to wherever the passengers actually are. We place that extra representable value right on the dominant outlier tail, eliminating the clipping completely, all while keeping the 0 point strictly at 0. And the absolute best part? I mean, the real game changer here? This entire solution requires zero additional inference cost. Since we aren't adding any complex 0 point math or disrupting those crucial vectorization patterns, you get the accuracy protection of an asymmetric quantizer with the 2.45 times throughput speed of a symmetric one. It is a total win-win for deployment.
Okay, theory is great, but running it through massive language models is another story. Let's look at section 4, proof in the performance.
So the crucial takeaway here is that this isn't just some tiny, obscure optimization. Theoretical analysis confirms that this signed ABS-max grid minimizes the upper bound on L2 quantitation error. And this mathematical condition holds true for a staggering 88 to 99% of weight groups across pre-trained large language models at low bit widths. For the vast, vast majority of your model's neural network, simply flipping the sign perfectly aligns the extra representable value with the dominant outliers. Now you might be wondering, what about those edge cases? For that remaining small percentage, say 1 to 12% of weight groups where the condition isn't perfectly met, the system doesn't just break. It safely and elegantly falls back to the standard positive scale. This ensures absolute numerical stability across the entire model without triggering assertions or propagating any not-a-number errors during inference. And they didn't just test this in a vacuum. The researchers empirically validated the method on massive, state-of-the-art architectures, including the QN3, QN3.5, and Llama 3 families. The results showed consistent perplexity drops and measurable improvements in downstream few-shot accuracy compared to standard unsigned quantizers. And remember, these gains come purely from reducing quantization error. There are no architectural changes to the models themselves, no additional training steps required. It's basically free intelligence, reclaimed right out of the compression process. So, how do you actually put this to work? Let's move to our final section, next steps for developers. If you're building AI applications right now, here is your direct 5-step blueprint. First, audit your inference engine's backend. Check if engines like llama.cpp or VLM support sign scale parameters. Most modern kernels already compute scale times weight, so adding a sign bit requires minimal changes. Second, update your post-training quantization calibration pipeline, specifically to replace standard ABS-max with this signed variant. Third, benchmark on your specific target hardware to verify the sign flip doesn't introduce branch mispredictions. Fourth, monitor your edge cases to ensure your error handling gracefully manages that fallback to standard positive scales. And fifth, integrate this with existing workflows. This method plays incredibly well with weight-only quantization and can be tested right alongside things like layer norm and KV cache compression. For you engineers out there updating your pipelines, here is the exact formula to implement. You compute the scale as the sign of the dominant tail multiplied by the maximum of either the absolute max or the absolute min. You then simply store that sign alongside the magnitude. It is a stunningly elegant, incredibly lightweight update to your existing codebase that yields immediate downstream benefits. Which leaves us with one final, absolutely critical question. Is your inference engine ready for signed scale parameters? We've seen how standard symmetric quantization forces a brutal choice between speed and accuracy by stranding an extra representable value on the wrong side of the grid. But by simply flipping a sign, signed symmetric quantization reclaims that lost accuracy at zero runtime cost, unlocking peak efficiency for the next generation of 2-bit and 4-bit models. It's time to look under the hood of your deployment pipelines. Thanks so much for joining me for this explainer, and I highly encourage you to check out the reference implementation and benchmark this on your own hardware.